So today we look at section 11.3, the integral test and estimates of sums. So we will begin with an example, with two examples that we looked at last time. So we have seen the following sums. Okay, we calculated that this converges and actually equals to 1, okay? And we've seen this. This is the geometric series, and it also converges. The reason we were able to establish the fact of convergence was that we were able to calculate, so for both of these, we calculated the term Sn, a partial sum for 1 to n of an. We derived the formula for that. And then we took the limit. If the limit is finite, it converges. If it's infinite, then it doesn't. Okay? So we were able to do this. But this is very rare. Actually, for most of the examples, you cannot so easily derive the general expression for the partial sum. But the question remains, does a given series converge, right? And sometimes, and very often, you can answer this question without having to do this, okay? Very often we cannot do this, but we can say that the series converges. So one example, which looks very simple, looks like this. One over n squared. It's 1 over 1 plus 1 over 2 squared plus 1 over 3 squared, and so on. Okay. So let us draw this sequence. Okay, so we have 1, 2, 3, 4. Like this. And the value here is 1. The value here is 1/4. The value here is 1 over 9. And the value here is 1 over 16. Okay, so it decays quite quickly, like this. And I also want to draw a continuous curve which corresponds to the function y equals 1 over x squared, right? So the summation here is this number plus this number plus this number plus this number. And we also have this function, and we can calculate the integral, say from 1 to infinity of this function dx. There must be a connection, right? How can we see that there's a connection? First of all, let me represent the summation geometrically. So we have to take this number. Let's multiply it by 1. So let's write it like this. 1 over 1 times 1 plus 1 over 2 squared times 1 plus 1 over 3 squared times 1, and so on. So I'm going to multiply each term by 1. I have the right to do that. And 1 represents the base of these rectangles. So this is the first rectangle. This is the second rectangle. This is the third rectangle. And so on, right? So this is like creating a Riemann sum of this integral by taking, first of all, the integral is infinite. It is improper. It goes all the way to infinity, but that's fine. And also, we don't want the base of rectangles to be very small. We don't want them to be infinitely small. We actually want them to be 1. because we want to multiply each of these numbers by 1, and that gives me the exact value for the series, the summation of the series. Okay? So we have the area of the shaded rectangles, and we can see that as we add them up, the answer is going to be related to this integral. So let me write it like this. Let's split this sum into the biggest rectangle, which has the area 1, area, plus the rest of them. Okay, I can do that. I split off the first one, and then I add up all the rest. And so the first value is, of course, finite. It's equal to 1. I'm not going to worry about it anymore. How about the infinite sum that remains? I know that the sum of all these rectangles is going to be less than the integral of the function 1 over x squared, because it completely is contained underneath it. So it's less or equal to 1 plus the integral from 1 to infinity of 1 over x squared dx. So the proof is geometric, right? The desired expression, the desired infinite sum is 1 plus the rest of them, 2, 3, 4, and so on. And that's completely contained underneath this curve. Why did I have to split off the first one? Because my function has a bit of a problem at 0, right? So I don't want to deal with this function in this region. So I just consider this separately and start integrating from here. Okay? Now, do you remember what happens to this improper integral? Does it correspond to a finite number, or is it an infinity? This is convergent because p is greater than 1. So let's actually prove it again. So consider an integral from 1 to infinity, 1 over x squared dx. Let's convince ourselves that it's a finite thing. So this is a limit as t goes to infinity of an integral from 1 to t, 1 over x squared dx. Now I have to take this very simple antiderivative. So it's 1 minus 1 over x, evaluated at 1 and t. Okay? So this is the limit as t goes to infinity of what? Minus 1 over t plus 1. And this is, of course, a very simple limit. When t goes to infinity, the first term disappears, and the answer is 1. So this converges. So I can conclude from these calculations that my whole series, 1 over n squared, is less or equal than 1 plus 1 is 2. Okay? Which means that the series converges. Okay? So by plotting it and seeing that it completely fits underneath a curve that converges when you integrate it, I can conclude that the series converges too. Questions? Okay, let's do another one. Again, we are going to relate. Oh, and by the way, so we can conclude that it converges, but we don't know what it's equal to. Okay? The answer is not going to be the same. The answer for this one is equal to pi squared over 6. Okay? And that's difficult to prove. So here we don't worry about that, but we can say that it converges, it is equal to a finite number, and that's usually what we need to know. Okay. So another example. Let's look at this type of series. Okay, 1 over square root of n. What is the corresponding integral that we're going to consider? 1 over square root of x dx. So if this integral were to tell us anything, okay, we have to recall the behavior of this guy. Do you remember what this does? If I integrate it to infinity, this diverges. So if I show that this is less than this, that would tell me absolutely nothing. It would tell me that it's less than infinity, and I don't know if it's a finite number or an infinite number. So perhaps it's bigger than this, in which case I would be able to conclude that it diverges too, right? So let's try to arrange our picture in such a way that this is bigger than this. So we go again 1, and it's possible to do, okay? How do I arrange it? So this is square root of 1. This is 1 divided by square root of 2. 1 over square root of 2. 1 over square root of 3. These are the members, the terms of my sequence. Okay? And I draw a line through them. The line is y equals 1 over square root of x. And somehow I have to sum these up. So why don't I complete them like this? I'm going to go like this, and like this, and like this. Remember the right-hand rule and the left-hand rule? Depending on where I estimate my function, I could draw my rectangles underneath this thing or above. So here I choose to do them above. So starting from here, my discrete sequence is always greater than the area under the curve, because it contains the curve completely inside. Okay, so I can say that the sum 1 over square root of n over square root of n is greater than an integral of 1 over square root of x, which is equal to infinity, diverges. Therefore, I conclude that the whole sequence diverges too. Okay.
Why put a 1 on top of the summation?
So I could do either. So I could say that I could do it like this, by doing this. And I could prove that some part of the sequence is smaller than this quantity. But that would give me zero information. It would tell me that it's less than something that's infinite. So that's uninformative. So I tried to estimate it in the other way. I built my rectangles on top of this decaying function. Okay, I can do it either way. So this way, I can see that the continuous function is hiding completely inside this. So if the function diverges, then the sequence diverges too. Okay, so the
No, 1. Oh, a summation, you put a 1. To the right? Yeah,
Here.
on top.
Oh, I'm sorry. Was that your question all along?
Yeah.
Sorry. Yeah, that was a typo. That would just be equal to 1. Okay. Fine. So this allows me to formulate a theorem that we'll use to learn about convergence of various sequences. So the integral test. Oh. So there are a few assumptions that have to be satisfied. So suppose that f is continuous, positive, and decreasing function on a semi-infinite interval like this. And we say that the members, the terms of my sequence, are related to this function. Okay. Then we can say something definite about the convergence of this series. So converges, and this is a mathematical expression, if and only if the integral of f converges. So we will expand. There are two statements. If the integral converges, then the sequence converges. And if the integral diverges, then the series also diverges. So simply put, there are many cases where this summation is very closely related with the improper integral. If the interval converges, then the series converges, and if the integral diverges, then so does the series. Okay, but you have to be careful. Continuous, positive, and decreasing, right? We could only build those squares in the manner that we did for a decreasing positive function. This construction would not even work for a non-monotonic function. So let's do some further examples. So to use this test, we have to know that the function is positive and decreasing. So the first example is like this, n squared plus 1. Okay. The question is, does it converge or does it diverge? So we look at f of x. Does this function, clearly it's positive, right? That's good. Does it decrease or not? Yeah, it's pretty easy to see that as x increases, this function decreases. So to answer the question of convergence for the series, all we need to do is integrate. Okay? So we're looking at the integral from 1 to infinity of this function. This is an easy one, right? So let's first rewrite it as an improper integral, like this. And then we take the antiderivative. So tangent of x from 1 to t. So we have tangent of t minus pi over 4. What's the limit as t goes to infinity of the arctangent? What's the arctangent of infinity? It's pi over 2, right? So pi over 4. Converges. And that's it. We're done, right? We can say that the sequence behaves, the series behaves in the same way. So we can say that the series n squared plus 1 also converges. Okay? Questions? Question?
Just for that.
Uh-huh.
How can you state that the summation is bigger than the interval?
So here we look at the area of the rectangles that are shaded. Okay? So clearly by construction, each of the rectangle contains the line inside. So on one hand, we see that the shaded area is greater than the area under the curve. On the other hand, we notice that the shaded area is equal to this. Because what is this? This is 1 over 1 times 1. This is 1 over square root of 2 times 1. 1 over square root of 3 times 1, which is just this. The trick is to arrange the bases to be equal to 1. Okay, so the area of the shaded shape is just the summation of these values.
So how can you switch between left and right?
So it all depends on how you arrange those rectangles. So this picture shows you two ways of doing it. You can do it like this or like this. You can complete, so for each point, you can either, basically for each interval, for each integer interval like this, you can either use the value on the right, like this, or the value on the left, like with the left-hand rule and the right-hand rule for the Riemann sums. And you can use the one that you want for this one. You can either make it bigger than the function or smaller than the function. And it will never change because the function keeps decaying. If the function did this, that would not work at all.
So it doesn't matter what rule you use, like right now.
So we used the left-hand rule here to show that this is greater than a divergent thing, so it diverges here. In the other one, we used the right-hand rule to show that it's less than a convergent thing. If we did and that was the informative way, we could say that this is smaller than something that diverges, but it would give us no information. Okay, so we can try both and see if it logically gives me any information. Both will work, but one of them will give you a result, and the other will tell you, oh, it's less than infinity. And if it's less than infinity, it could be either infinite or finite. Okay? So both are correct, but one is informative and the other one is not. And the general rule is that you don't even have to do this anymore. You can just use the theorem. Okay, this replaces all of those constructions by saying that if the function satisfies these properties, then the integral and the series are closely related, exactly as is stated here. And it works both ways. Question?
Since we know that the function is continuous and positive and it's decreasing, do we still need to use the integral to define whether it's convergence?
Yes, so the function is continuous, positive, and decreasing, but this integral can be either divergent or convergent. So you absolutely have to study this integral to say anything about the series. Okay. Question?
So if it makes like a bend or something, then we can't use that.
So this is a very good question. What happens if the function makes a bend? And the answer is yes, you can still use it, but with caution. So let's suppose that the function is like this. Okay, so up to here, you cannot use it. But starting from here, and for all of eternity, you can use it, right? From here and up to infinity, it's a decreasing function. If it keeps making turns to infinity, then that's no good. But if it has a finite number of turns and then it becomes decreasing, then you can use it. And this is our next example, I think. So let me give you that example. Oh, okay.
You already said the sum is convergence. Why do you put convergence or divergence in the bottom? So
If the integral diverges,
but on the top, like then,
here,
yeah.
so this is a mathematical statement. So this last sentence, okay, is a concise way of saying this, 1 and 2. If you can either read this or you can read this. A mathematician will tell you the series converges if and only if the integral converges. And he can stop and that's it. Okay? Or you can expand and say, if this converges, then this converges. If this diverges, then this diverges. These are synonymous statements. This is more concise but less clear. And this is longer, but it tells you everything you need to know. Okay. So I want to address this question in the next example. So let's look at this. Log n over n. Okay? So we'll look at the function f of x, which corresponds to this log x over x. And this function is not monotonic. Okay? So it's not even positive. Okay, it's going to be positive for it's greater than 0 if x is greater than 1. That's good enough. Okay, that's good enough. But what does it do in terms of the derivative? So to study whether this function decays, we look at the derivative, of course, right? If the derivative is negative, we're good. So we have to calculate the derivative of that. So 1 over x times x, whatever that rule is, log x over x squared, okay? And we simplify by dividing by x. So I have 1 minus log x over x squared. Okay? So what can we say about this quantity? X squared is positive, but 1 minus log x, is it greater than 0 or bigger than 0? So I can say if log x is less than 1, this greater than 1, f of x decays. Okay? So this inequality, what does it amount to? X is greater than e to the 1, right? F decays. What is e? 3.7 type thing, right? Right? So starting from about 4, this function behaves in the way that we want it to behave. So in fact, what it does, if you plot it, I don't want to worry about that function for negative values. So at 1, it is 0. Then it experiences a maximum at e, and then goes down, this function. So it's not, by no means is it a monotonically decaying function. But it is if you restrict yourself to the values of n starting from 4. Okay. So what can we say about the sum? We have log n over n. So we can say that we have that thing from 1 to 3 plus, and this is only 3 terms, 1, 2, and 3. And then we starting from 4, we have an infinite sum with a corresponding function that decays. Okay. So now this guy is going to behave like this function. And who cares about the 3 terms? They cannot be infinite, right? This is just some number. So what we have to worry about is the infinite part. So this is what we compare with this function. And starting from x equals 4, this function is decaying. So we need to calculate the integral of that function. So what's the integral of log x over x dx? So limit from 4 to t log x over x dx. How do you evaluate this integral? Substitution, right? Because 1 over x is a derivative of log, so u is the log. The integral is u squared over 2, and then we recall that u is the log. So you have log x squared over 2, limit t goes to infinity, evaluated at 4 and t. Almost done. So I have log t squared over 2 minus log 4 squared over 2. What's the answer? What's the answer here? I have a log of t when t goes to infinity. What does it do? Infinity. So the whole thing blows up, right? So the whole series, log n over n, diverges. Okay. So we were able to use this theorem starting from a finite number because we proved that after this number, the function decays. And to the left from this value we have just 3 or a finite number of terms which are finite. So they're not going to influence the question of convergence. Questions? Okay, so one more important result, very important example. Or actually, let me move on to the next topic, and we'll see how we do. So, estimating the sums of estimating the sum of a series. Okay. So this is what I want to talk about. So when we calculate something like this, let's suppose we have a computer. And the computer can add a lot of numbers. For instance, 100 of them or 1 million of them. What the computer cannot do is it cannot add an infinite number of terms, right? So we have to cut it somewhere. And if the sequence, if the series converges, then presumably if you sum up a lot of these, you get an answer which is pretty close to what the actual value is, right? But how different is this estimate going to be? So we're going to say that we're going to use, let me use the index I here. Let me sum up only partially this series. And then I'm going to look at the rest. Okay. So this is what I can calculate with my computer. And this is the infinite number of terms that are left. So presumably this is somehow small. Okay. And let's call this Rn. Call this remainder. If we can estimate this remainder, if we can say, okay, this is less than 0.1, then we know that the finite sum, the partial sum that we calculated, is not too different from the actual infinite sum. Okay. So to estimate the remainder, we're going to look at some pictures again. We're again going to assume that the function f is decreasing, okay? And we're going to have the following picture, n plus 2, and so on. So, like before, I'm going to draw two pictures. And we'll do it side by side so everybody can see. So let's draw an identical function. I'll try to draw an identical function. Okay. So this is n plus 1, and so on. Okay. So here I'm going to complete like this on the left. And here I'm going to do it on the right. Okay, so this is the same thing. This height is an plus 1, an plus 2. This height is an plus 1, an plus 2. Okay? And I'm going to write down inequalities. So Rn is the sum starting from here. Okay. It's an plus 1, and so on up to infinity. This is less than the integral by construction. And I'm integrating the function f of x dx starting from n to infinity. Here I have the same remainder, an plus 1, an plus 2, and so on. And here you can see that by construction these rectangles are above, so it's greater than the integral starting from n plus 1 to infinity, f of x dx. Okay. So these are very similar inequalities, except the sign is different. And the limits of integration are different. Here I'm integrating from n, right? I'm starting from here. And here I'm integrating from n plus 1. So if I combine these two, I can put two bounds on the value of n. Okay. So if I want to know what the error is of my approximation, I have to calculate a couple of integrals from this function. And I will give you an example immediately to demonstrate the power of this method. So let's consider a particular example. So approximate this series e to the minus n with n equals 5 terms, and estimate the error. So, okay, let's suppose that I'm too lazy to add up an infinite number of these. Okay, I only have time to add 5 of them. So my approximation is going to look like this: from n to 5, e to the minus n, okay, whatever it is. And the remainder, r, is what is left, from 6 to infinity. This is the error of my, this is the price I pay for my laziness. If I only have time to add up 5 of them, how much do I lose with respect to the actual precise answer? So this remainder is my error, and it has to be less than this integral, right? According to the theorem. So this is what I need to calculate. We have to calculate an integral from 5 to infinity e to the minus x dx. By the way, I forgot to say that before we do this, we need to check that this function, e to the minus x, is positive and decaying. But it's pretty clear that it is, right? It's a positive function that decays. It's a negative exponent. OK, so to estimate this remainder, we calculate this integral. And that is very easy. OK, let's do it properly. Limit st goes to infinity from 5 to t e to the minus x dx. Limit. The antiderivative is minus e to the minus x from 5 to t. Okay, so what's the limit? You can see the negative exponent, right? As t goes to infinity. What's the limit of the first term? 0. Question?
I'm a little bit confused. So you said the remainder went from 6 to infinity.
Yes, so I take into account the first 5 terms, and the next one, the one that I didn't take into account, is 6, 7, and so on. But the estimate on the remainder on the right is from 5, and this would be from 6. Okay, if I want to estimate it from below, I would use 6. This is n, 5. Okay. So what's the limit here? This is 0. So this is e to the minus 5. And this is equal to 0.0067. So the error is not so bad. Okay. Instead of an infinite number of terms, I only added up 5. And the difference is a very small number, especially compared to the sum that I obtained. So let me see if I calculated this. So if I calculate this sum, it's going to be a number approximately 0.5. So compared to this difference is minuscule. Okay, so it tells me that my approximation is pretty good. Okay, So the next question is, how many terms do we need to take into account if we want a precision, a given precision? So how many terms do we need to sum for accuracy of at least 0.001. So you can see that this is not quite enough. 5 is not quite enough because the error that I got here is 0.006. So it's about 7 times bigger than I want. I want to reduce the error. How many terms do I need? So I know that r is less than an integral from n to infinity e to the minus x dx, right? So this is what I need to calculate. I want this number to be less than this. So I have an integral from n to infinity e to the minus x. I can repeat exactly this computation, but instead of 5, I have n. So this is equal to okay, so this is an estimate of my remainder, and I want this quantity to be less than 0.05. So we want e to the minus n to be less than 0.001. I take the log, I get minus n is less than the log of 0.001, or minus n is less than minus, I calculated this at home, 6.9, or n is greater than 6.9. So 7 terms would be enough to calculate this with a precision of 0.001. Okay. So the question.
So to calculate the remainder, should we always use like the above one?
If I usually want the remainder to be smaller than something. It's just practically speaking, I want my to reduce my error. So my greatest allowable error is, for instance, 1%. So it has to be smaller than 1%. So this estimate is more useful practically. Okay. More questions? Okay. So the last point that I want to make is there is a way to approximate there is a way to estimate the sum of a series. So this formula estimates the remainder. How can we estimate the sum? So I take this formula. Okay. Actually, let me just do it here. I'm going to add Sn. Add Sn to each side. So I have Sn plus this guy, Rn plus Sn, and this is n to infinity f of x dx plus Sn. And I notice that this is a partial sum plus remainder, so this is actually S, my exact infinite sum, okay? And on the left and on the right, I have two quantities that I can calculate without having to add up an infinite number of terms. Because this quantity contains a finite sum plus an integral that I can calculate. Here I have a finite sum plus an integral, and here I have this expression that I may not have a formula for. This is my infinite summation. Okay, so I obtain the bounds for it, which are very useful. So let's do the example. estimate the same infinite series e to the minus n with n equals 5 terms. How close is my answer if I only add 5 terms? So we know that, so I'm going to have to calculate the left-hand side and the right-hand side of this inequality, okay? So I need the integral from n to infinity e to the minus x dx, that's e to the minus n, and the integral from n plus 1 to infinity e to the minus x dx, that's e to the minus n plus 1, right? So writing down that formula, Sn plus e to the minus n plus 1 is the lower bound, and S and S plus e to the minus n is the upper bound for my actual infinite summation. So what is Sn? It's e to the minus 1 plus e to the minus 2 and so on, plus e to the minus 5. I calculated this by using a calculator, and it's given by 0.578. Okay. Now I need this one. This is e to the minus 6, given by 0.025. This is e to the minus 5, 0.00067. So I obtained bound for this infinite sum. So let me write that down to summarize. E to the minus n. So I have no idea what this quantity actually is, but I know that it's greater than something, and I know that it's smaller than something. So here I add these two. I get 0.5805. And here I have 0.5848. Okay? So by using only 5 terms, I was able to create a window that tells me that my actual infinite sum is greater than this number, and it's smaller than this number. And it's pretty tight, as you can see. Question?
Yeah, for the inequality, why did you have the n plus 1 is less than the n?
Here?
Yeah.
Okay, I unfortunately erased the picture. So you saw that very faintly on this whiteboard. You can see 2 pictures. They have the function, and they have the values, okay? And I can complete it on the right or on the left.
Yeah.
And if you look at this picture, in one of them, the integration starts with n plus 1. And on the other one, the integration starts with n. The picture is in the textbook. N plus 1 is greater, but because the function decays, this integral is smaller. You integrate over a smaller area. Okay? Thank you.